Hi everyone, I'm Professor Burgasser, and in this video we're going to be looking at moments of inertia and describing the shapes of objects and quantifying the shapes of objects. We're going to introduce this new physical quantity which describes the distribution of mass of an object and also describes how an object resists the torque applied to it to cause an angular acceleration. We're going to see it's the equivalent of mass when we apply a force to an object, and that causes a translational acceleration. Now, remember that we're talking about how we spin objects like a wheel. We're applying a torque, which is an offset force, and we can calculate that torque, the direction and the magnitude, using the right-hand rule. So again, if we point our first direction with the coordinate from the center of our mass, or the origin of our coordinate system, and cross it into our force, we get a direction for our torque. And in this case, that's going to be a torque that's pointing away from you and into the screen. And also, as you're applying this force, you can imagine this is going to start to spin the wheel around this direction. And of course, this hand motion also provides the direction for the angular acceleration. So that force applied at that point is giving rise to both a torque and an angular acceleration in the same direction. And it suggests that there is a, of course, direct relationship between these two. Now, again, as an analogy of Newton's laws, we define torque as r cross F, and it's the force equivalent to translational motion, but applied to rotational motion. And so we're going to have the same constant between torque and the angular acceleration, in this case a constant that's related to mass, and that's going to be our moment of inertia. Now, just looking at the units, remember that the units for torque is going to be the units of the displacement, which is in meters, and then the units for force, which is mass times acceleration, kilograms meters per second squared. So for these units to work out on both sides, because the angular acceleration is in units of inverse time squared, it's radians per time squared, but radian is not a dimensioned unit. In order for that to work out, you have to have a moment of inertia that is units of kilograms times meters squared. So it's clearly not just the mass, there's some other component to it. And in this video we're going to see how we calculate that component. Now, just as an example, let's start with a very simple case of just having a point source in which I'm applying a force, and that force is perpendicular to the distance between the origin of our coordinate system and where the mass is. So this is going to give rise to a torque, of course, because this force is applied perpendicular to the offset. So it's very easy to calculate this. Again, we can just use our right-hand rule and move the radius in this direction and force in this direction, and that's going to apply a torque that's now pointing toward you from the screen. If we just look at the magnitude, the absolute value of that vector, since this is a perpendicular force to the position vector, it's just going to be r times f. The sine theta term is sine of 90 degrees, and so that's just 1. Now, remember from Newton's second law that force is mass times acceleration, so that gives rise to the torque being mass times the position offset times the acceleration. And if we're looking at this as an angular acceleration problem, recall when we defined our angular rotational quantities, we could relate the angular acceleration, the physical acceleration, at sort of the angular direction to the radius times the actual change in the angular rate. All right, and that's the alpha term there. So if we substitute in those expressions to get out our actual radians per second squared angular acceleration, we see that we get this term out in front, which is mr squared, and that has the right units, mass times length squared, to be this moment of inertia. So we first get our first clue of what a moment of inertia is, at least for a point source, is the mass times its position away from the origin of our coordinate system, our rotation axis, squared. And this is starting to tell us that the moment of inertia is really measuring the distribution of mass in space. It's measuring how far away the mass is from our rotational axis. Now let's expand our analysis to include a system of masses that are all rotating around a common rotation axis. So you can imagine that this is maybe a bunch of little masses that are placed on a table, and the table is sent spinning around. So let's assume that this table is actually not just spinning, but actually increasing its spinning rate. That's our angular acceleration. We can relate that angular motion, again, back to the linear translational motion for each of these objects, at least at a particular point in time, as the product of the radius from the rotation axis out to where the mass exists and the angular rate. And again, because of Newton's second law, that acceleration is also equal to the force divided by the mass. Now, schematically, of course, we can measure these radius by just looking at position vectors from our rotation axis, or center of our coordinate system. Multiplying by the angular acceleration is going to give rise to the actual physical acceleration, which of course is tangential to the rotation at the position from the rotation axis out to the mass. So you get all of these angular accelerations adding together to all these translational accelerations, which point in all sorts of different directions. But we can calculate the torques for each of these masses by simply measuring their torques of individual masses and adding those together. So that looks like this. The sum of the torques is just equal to the sum of the products of the separation from the center of mass times the force that's acting on that object. And I should say, if these are masses sitting on a table, that force is probably something like friction force that's keeping the object moving in a circle. Those forces, multiply those together, you're going to get, replace the force with mass times acceleration, and you get a sum of, again, the mass times the position times the linear acceleration. And much the same way we did last time, we can replace that with the radius times angular acceleration. But notice that that angular acceleration is the same for all of the objects, right? We're rotating the entire system at the same angular acceleration rate. So the only thing that depends on the individual masses is the sum of the mass times their position from the center rotation axis to their actual coordinate squared. And so that, again, is going to be a measure of the resistance to angular acceleration by torque, and that's another expression for our moment of inertia. So more generally, if we have a system of masses, we just sum up all of these products of mass times position squared, and again, it's the mass of the system and then the position that's perpendicular to the rotation axis. Adding up all those pieces gives you the total moment of inertia of our system. Now, that's for the case of just little individual masses. Of course, if we now fill in our space with all sorts of mass that uniformly covers, say, our table, what we have now is a disk, and we can also calculate the moment of inertia for that disk. Now we're going to be applying Newton's trick to look at infinitesimal little masses and then adding those up as an integral. And so another expression for the moment of inertia, at least for smooth continuous objects, is the integral of the position squared, again, perpendicular position from the rotation axis, integrated over all of the masses in the object that we're looking at. Now, our expression for moment of inertia is just one more expression that describes the distribution of mass of an object. And we've already seen two of these already. One, of course, is just the total amount of mass of an object, and that's just adding up or integrating over our object and counting up all the pieces of mass that makes it up. We've also seen the center of mass, which is the weighting position of all the masses in our object. And of course, that center of mass is where body-centric forces act, like surface gravity or weight force. Now we're seeing another moment of mass, and moments are these sort of adding up multiple scales of position squared. This moment of mass, or moment of inertia, describes the broader distribution of mass in space, because it depends on r squared. And again, it's related to how much resistance there is to rotate an object given a force. Now we can use our expression for the moment of inertia to calculate the moments for all sorts of different various shapes. So you can do hoops that are just sort of rings of mass. You can do disks, you can do balls, all sorts of different common objects can be solved by just solving for the integrals. And we'll have another video to show how we actually use those integrals and summations to solve for these various shapes. Now, one thing I'll point out here is that you'll notice that the moments of inertia for, say, a hoop and a full cylinder are the exact same value. And that's because this moment of inertia depends only on the mass that's perpendicular to the rotation axis. So if I add a bunch of hoops together, in fact, I'm just adding the same moment of inertia distribution, but divided by the number of hoops times the fraction of mass in each of the hoops. So you end up adding up exactly the same value no matter how long along the rotation axis you're adding. So it doesn't matter how long the object is along the rotation axis. What really matters is the mass distribution perpendicular to the rotation axis. Now, it's important to remember that the moment of inertia is defined about a particular rotation axis. So if we take an object that looks a little bit like a hoop and we spin it about the center of mass in this direction, that rotation motion requires a moment of inertia which is the mass times the radius of our hoop squared. Now that's only true if we're circling around this way. If we change our rotation axis and rotate our object in this direction, in fact we get a different moment of inertia, a smaller moment of inertia, because the mass is not as far from the rotation axis as it is in this case. In fact, it's half as distributed as the case where the hoop is horizontal like this. So whenever you're defining your moments of inertia, you have to make sure that you know exactly what the rotation axis is and compute it for that rotation axis. Now, not only is the orientation of the rotation axis important, but so is the location of the axis with respect to the object in space. So if I take my hoop object again, I can spin it about its center of mass, and that gives me a moment of inertia that's m mass times radius squared. But I could also take this and spin it about a point along its edge, like this. That's going to be a different moment of inertia because the mass is further away from the rotation axis, and that's going to have a very different distribution and a different resistance to the angular motion that I'm applying. I could take it one step further and suspend our object from a string, like this. And in that case, we're going to have an even more different moment of inertia because the mass is now quite far away from the rotation axis, which is up here. So how do we go about calculating the moments of inertia for these offset axes? Well, we can use something called the parallel axis theorem, and that tells us, and that we can do this by actually computing the moment of inertia directly, that the total moment of inertia for an object that has an offset axis is equal to the moment of inertia for that axis going through the center of mass, which is the smallest moment of inertia, plus the mass times the perpendicular displacement from that axis. And so those are the two terms here. And of course, as we get further away from our center of mass, the moment of inertia, the difficulty in order to swing these objects, becomes greater and greater. There's more resistance to the torque for angular acceleration. So in the case of our swinging hoop, the moment of inertia is just simply the mass times radius squared for our center of mass motion, plus the mass times this distance squared between our pivot point and the center of mass. So it's very easy to calculate for these motions at different positions and different axes. Now, this combination of different shaped objects and being able to shift the rotation axis in different spaces allows us to build up the moments of inertia for much more complicated objects. So let's take an example of just a barbell. If I model this as just two spheres and a bar connecting them, well, this is really the sum of the moments of inertia of three objects. Two spheres that are offset from the rotation axis, so they have a parallel axis theorem they have to apply there, and the bar in the middle, which we're rotating about its center of mass. So you can see here that we're just adding up these different terms because that moment of inertia is just a sum over the mass. So I can just keep adding mass and structure to my object and just compute what the total moment of inertia is. So this is really a way we can build much more complicated objects. And of course, in nature, we do have much more complicated objects. And so this is how moments of inertia, for example, are calculated for things like molecules. So that sort of microscopic scale, we're interested in the rotation of molecules because that gives rise to absorption of light due to that rotation. You may also, if you're a sports designer, may be interested in the moment of inertia of a tennis racket as you're spinning around. And we can model that using this moment of inertia framework. As an astronomer, we study objects that have odd shapes, such as asteroids, which do rotate in space. And so to understand that rotation and how much force and energy was put into the rotation of this object, we have to calculate its moment of inertia. And again, we can do this with a model that builds up different types of objects together to make our complete three-dimensional body. So to summarize, the moment of inertia is a physical quantity that describes the mechanical resistance to torque, the resistance to angular acceleration, but it also describes the three-dimensional distribution of mass in space. And so we can see this in the calculation shown here, where moment of inertia features as the sort of scale factor between angular acceleration and torque, and it's also calculated as the sum of the masses times their positions relative to the rotation axis and perpendicular, I should say, to the rotation axis squared. Now, the moment of inertia depends on what rotation axis we're talking about, so it depends on the orientation of our object with respect to the rotation axis, and it depends on where our object is relative to our rotation axis. And we can use for the latter the parallel axis theorem to compute the total moment of inertia for an object that's offset by just adding the mass times that offset distance squared. We're going to see some more examples how we calculate moment inertia in some of our other videos. But keep in mind this is just a number that we have to calculate for an object to understand its rotation rate. Once we can calculate it, we can go ahead and treat that as an effective mass for our kinematic equations.